Hi everyone, my name is Philip. Today I'll be talking about how our team built self-service serverless data platform at Amazon and how we used it to scale our platform to support hundreds of datasets and tens of teams. So the agenda of the talk will be as following. So we'll first talk about PXC DAS, which is the name of the data platform in this architecture, what it represented itself before we started implementing the self-service. Then I'm going to talk about why we need self-service at all. What problem did we try to solve with that? The core part of their talk will be the implementation walkthrough. So I'll talk you through some design diagrams and how we implemented, what decisions did we make, and why. The last bit will be the results and learnings that we'll share with you as a result of this project. I'll do first some bit introduction about myself. So yeah, as I said, my name is Philip. I'm a senior engineer at Amazon. I was working 3 years on the team, which was building PXC DAS. I then moved to another team, which starts building internet search, with trying to apply generative AI in the space. And this month, I'll be also joining Prime Video in London. So if you're in London or LBB, feel free to reach out to me. I'll be happy to meet. I have a background of iOS development. So I spent 3 years building iOS applications before I joined Amazon to work on the backend role. In my free time, I do windsurfing and bouldering. And yeah, our disclaimer is, I want to warn it's all my thoughts here on my own, even though I represent the work that I did in Amazon at my time. On the team that PXC DAS, all the thoughts and conclusion are my opinion, and I'm not an official Amazon representation here. Yeah, so what is a data platform? What is PXC DAS? So data platform as a software basically sits between your other teams who have their own tech stacks, and it helps organization or a company to build data-driven applications and apply data to make data-driven decisions. Data platform facilitates data collection, storing data, processing that, and analysis downstream, and yeah, application of data, obviously. And ultimately, it helps to exchange data between different applications and teams at scale. PXC DAS, which stands for People Experience Technology Data as a Service, where People Experience Technology is an organization which has working on technology for chat space within Amazon. So the PXC DAS itself has 2 sets of the customers, and all of those are internal. So we have customers which are data producers and data consumers. Typically, a data producer would be a tech team who owns their software application with some backend and maybe a web application, web portal or web UI. So this application would emit some real-time data to us, and we will share this real-time data with other teams, with data engineers and data scientists. Other data scientists and data engineers are the data consumers who get data from PXC DAS, and also not more frequently, since development of platform, data engineers, data scientists started to bring their data back to PXC DAS, so ending this loop and becoming both producers and data consumers. Features. So feature set of PXC DAS that our teams built before we started working on self-service project are event ingestion. So we ingested data in near real time via API that allowed software applications to stream data to us. We had a schema validation and schema evolution as well. So our platform stored schemas of the data sets in the JSON schema format. We requested data producers to provide a schema upfront. So that's a bit different from maybe other data lakes that you see out there in the industry. So we had a schema on write pattern. One of the main features was our bulk export, where we transformed the data and exported it as a snapshots to object storage to S3. We also had a feature such as vending data via near real-time API and end user facing reporting when we had managed service that help non-tech people to build reports with our data that we had in PXDAS. Those features I'm not going to cover a lot in my talk, but I just mentioned here that it's something that we also did. We also had a bunch of features such as on-demand data analysis for data exploration and data investigations with AWS Athena, which is a service that allows you to run SQL-like queries, or in particular Presto, if you're familiar with that. And compliance automation, that's another problem that we solved. So yeah, I'm again not a big part of this talk, but just an example of what the type of problems we solved. The high-level architecture is as following. So on the left, we have data producer, on the right, data consumer. Data flows through ingestion service, where the customers send the data, and then it's multiplexed into a bunch of different destinations. Some of those were data lake, where the data was stored in S3 bucket, and real-time API, where the data was also managed through real-time. A bulk export service is further downstream of the data lake. It gets the data from data lake and exports it to data consumers. A core part of this diagram, which I wanted to stress, is the code repository. So we, in the first years of the PXDAS, we stored all the metadata, such as producers, schemas, configurations, so how different data sets needs to be exported in the code repository. That will be a core part of the that talk today. So we're diving into low-level architecture. So ingestion service, or a simplified version of that, is quite simple. So it had an API implemented by AWS API Gateway Service. We use serverless architecture, and obviously we also use AWS as a team in Amazon. So yeah, we use Lambda functions to handle requests of ingested data, and we put data on the Kinesis, which is similar to AWS service for Kafka, to stream data downstream into other internal services. API Lambda, when they received an event, use the JSON schemas, which were previously defined by data producers, to validate the data. So not only valid data will flow into the platform. That's how we solve the data quality problem, or one of the solutions. Data Lake, another part of PXDAS. So Data Lake received data in near real time through Kinesis. There was a Lambda that gathers data and wrote the JSON in the real-time S3 bucket. Each dataset had a different folder in S3. On top of S3, we had Glue Data Catalog. So for those who might have not worked with AWS, so Glue Catalog is a metadata repository for datasets in AWS. It stores only metadata about datasets, which are usually presented as Glue tables that describe the dataset name, schema, location in S3 bucket, and other meta properties. Multiple AWS services in AWS which want to query the data from S3 use integrated Glue Data Catalog to know where should they find the data and what fields they have and so on. So for example, as AWS Athena, as I already mentioned, Redshift, Glue, ETL, which is serverless Spark, and AWS, and so on. So we used JSON schemas from code repository to create Glue tables. A bit first about how we did it is down next slides. Data from real-time S3 buckets flew to bulk export service. Bulk export service, so yeah, it got data from real-time S3 buckets. There were a bunch of jobs which were running on schedule. And the jobs were snapshotting the data, transforming it if there are any transformation that the customer provided to us, deduping, and converting the format to something to the format that customer wants, for example, Parquet, CSV, TSV, and store this data in a snapshot S3 bucket, which was the main interface with their data consumers who wanted to get data in bulk. Code repository contained the configurations for how dataset should be exported, which configured and orchestrated the jobs that the bulk export service had. Let's talk a bit about customer journey. So let's say that your organization wants to create a report for a peer feedback application. Completely, just out there an example. Let's say we have two personas, Bob and Alice. Bob is a software engineer who has data in NoSQL database, such as DynamoDB. Alice is a data analyst who wants to process data in bulk. It works with Spark. She works with dashboards and wants to produce reports. So how will customer such as Bob produce data to PixCDAS. So first, it will create a ticket to our team. Tom, another third persona, an engineer from our team, had to pick up the ticket, contact the producer to know better about this use case, and update the list of data producers, which was also stored in file. Bob then would create a pull request with the schema of their dataset. Schema, again, was used by PixCDAS to validate the incoming data. So this was a crucial part of the onboarding. Bob created a pull request with a 3 export configuration as well. So it's a separate file, which needs to be also, submitted. Tom had to approve pull requests, merge them, deploy through the pipeline. And then Tom grants Bob access to published data. And Bob builds integrations PixCDAS ingestion API. So now the software application sends data or particular events to PixCDAS. Custom onboarding. So again, Alice here in this case creates a ticket to our team with a request to access the dataset. I forgot to write it in the slide, but actually Tom had to check with Bob if Bob's team is fine to share this data with Alice. It's part of their process where we don't want to share data with a bunch of teams to reduce the risk. Tom grants that permission access to PixCDAS S3 bucket to Alice's team. And now Alice builds data pipeline that generates weekly reports and dashboard. So that's not it. So after the first integration, both Bob, Tom, and Alice had more work to do. So interactions over time included for use cases such as schema evolution. So what if Bob now wants to add another field or move a field, update the description, or maybe there was a problem and now they need to restructure the data, maybe to introduce completely new version, stuff like that is what falls under the schema evolution. Data quality investigations are quite often Alice would spot something in the data, reach out to Tom, Tom will reach out to Bob, they will all sit together to find the problems with the data. Data consumers would probably there would be more than one data consumer who wants to consume your data set in large organizations. And so more onboarding the data consumers will have to be handled by Tom. As you might see, the problem is Tom is kind of sitting in the center here, having to handle all their operations. And that leads us to the problem statement. So what? So time to onboard one application is dataset could take up to 2 weeks. Team will spend time on reviewing their code reviews, pull requests, talking to figure out the use cases, explaining the features, deploying the changes, and in general, especially in the different time zone, the whole ticket communication could take quite long. It's the minor reviews that were also error prone because the schema evolution were handled through pull requests. It means that responsibility felt on our team to check how the schema changes that should not impact the consumers and that they are backwards compatible. Customer experience is not ideal for non-tech teams and non-tech roles. So teams who do not work with code repositories that much, pull requests and files, they might be struggling to produce data to the platform. And non-tech roles, people who don't work with code repositories will have problems with exploring the dataset catalog and finding what datasets we have and who owns them and so on, because all this metadata is stored in code repository. For our team, personal operational cost of onboarding and supporting datasets was quite high. So in Amazon, we do something like on-call, where an engineer, dedicated engineer, supports the ticket queue and ongoing operations and issues. And that cost was especially high because always there will be some onboarding going on or customer questions and customer actions and so on. So we back then decided we want to scale to support more teams and more organizations within Amazon. And we realized that our platform is not scalable to support tens and hundreds of teams and their datasets. The solution is self-service. I, before working on this project, didn't realize it's like a whole pattern for this, the whole definition for this approach. But according to ChatGPT, so self-service approach enables customers to access information, resources, and tasks independently without requiring assistance from humans. In our space, it means that producer and consumer need to exchange data without involving our team. So Tom will be busy doing something else, relaxing, or probably building out the features that our customers want. And yeah, that's how we came up with the idea that we need to build a portal. So previously, all the metadata was handled in the code repository. Let's build UI to display this metadata and help customers to work with this metadata. Bob will use the portal to register their application, to add datasets, provide the schemas, configure where datasets should be exported, grant permissions. Alice, as a consumer, would browse datasets, find request access to the dataset, and find dataset owners in that context, because in a large organization, when the multiple datasets have been shared between multiple teams, it usually could be quite problematic to find out who actually owns the data that you are dealing with and who needs to be contacted in case of any issues. Yeah, portal also allows to build more features in the future, like access metrics and data quality metrics, which I mentioned in the left bottom, will be the new features we could potentially we will in the future build with portal that will allow teams to view who accesses the data set and some generic and maybe custom data quality metrics such as number of rows or the size of data set and any other custom metrics we will in the future add as well. But it's not part of this talk, so I will move on. Metadata. So what talk about metadata? What is metadata? Again, simplified examples here. You see a list of data producers on the left, which has like team, name, and owner, and a list of AWS accounts, because most of our customers use AWS. Data sets as well. In this example, it's quite simple. So we had just name and versions. Schemas for datasets were stored as JSON schema files, so a special specification for schemas, which we used extensively, and we landed on that. One of the main reasons we landed on that is because we start with streaming events were in JSON, and JSON schema seemed like a logical way to validate the incoming data in JSON. So yeah, that's type of schema that customers will have to write and submit in a code review. It will sometimes have a review for code review and catch any issues. S3 expert configuration, one of the examples of expert configurations because it supported multiple. In this case, you will see here we will specify the transformation. History review will be an example of transformation where we stored all the data and vended all the data of the data set. There are other examples as well. And yeah, format here is also specified. So let's take a look how the metadata was applied before the introduction of portal. So as remember, Bob and Tom both make changes in the code repository with metadata. All the metadata we just discussed was stored there. And then we deployed this metadata through our pipeline. So our CI/CD pipeline, it was basically like a library that we deployed every change on. So with this metadata, we could update API gateway policy to grant producer permissions to publish data. We could update their Lambda code because Lambda function need to know what their data sets are, what the JSON schemas are. It was one of the dependencies in the Lambda code. So yeah, whenever a new data set is there, we need to update the code. Glue tables and glue data catalog. So when we add a new dataset schema, we need or update it. The glue tables need also to be updated. Again, it's something that our pipeline was doing. And other stuff such as orchestration of jobs, updated S3 policy were all applied by the pipeline. A bit more technical details here. That the way it was working is that we converted the metadata into CloudFormation templates and deployed this as CloudFormation templates. But yeah, it's something we could dive deep into the Q&A section if people want to. The introduction of control plane. So now what was previously handled by the pipeline and was, forgot to mention one important thing. So in this picture, you'll actually see another problem that existed in our platform, that not only the time took to handle the ticket and approve the code reviews and pull requests, but also the deployment. So we had a single pipeline at the time, which deployed all the changes from our customers, and it usually happened that customer wants to update the data set, but their code change would get stuck in the pipeline for multiple other reasons. For example, integration tests of the pipeline started failing, and we need to figure out why is that, and because of that, the customer is blocked. So we're introducing the portal. So let's handle all the metadata right now in a special set of services, which we'll call control plane. So control plane will take their metadata and apply it to the platform instead of doing that with the pipelines. Well, before we go further, I need to talk about another strategy or like architecture vision that we had at this time when we were implementing the self-service. So I mentioned we had a large pipeline, and even though we are logically split their ingestion service, data lake, real-time APIs, and other parts of Pixie DOS into services and models, they were still deployed in a single instance, and our team was growing in size. And we decided to engage into the microservice architecture and split Pixie DOS into a set of the services or microservices, depends on your definition, and deploy them separately. And yeah, we also wanted to solve that their development speed and user experience, development experience, because of, yeah, you need to work with large monolithic application, and usually it required investment for us to make sure the deployments are fast enough, iterations are quick, and you don't have to handle all the code base when you're making any changes. Yeah, I mentioned the team was growing in size. So yeah, we in Amazon value their independence of the team, and the teams should be small and handle only a subset of services. So if our platform grows, our number of teams we have is also growing. We want to handle those multiple teams, different parts of Pixie DOS, and don't depend that much on each other. And yeah, furthermore, we want to add more features such as ingesting data in bulk, updating reporting, the data quality as well, and so on. So because of that, we decided to build multiple control planes. So one alternative that we had was to have a large control plane that we had all the data from the portal and apply this to the whole platform. But again, because we wanted to move to PXT-DOS microservice architecture, if we had one large control plane, it would not fit into this architecture vision-wise. So it will be a large bloated control plane, which will be tightly coupled with all the different microservices. So because of that, our decision was, let's build a separate control planes for the Pixie DOS. One bit of the microservices architecture is thinking features is topics like bounded context and thinking about the domain of a microservice. That's what you usually need to do to make sure that your decouple the services is quite right. So let's talk about metadata a little bit. So in ingestion service, the metadata we had was limits on ingestion, so which will declare how many events the customers could send, the modes of ingestion as well, like the type of data people send, and in general in bulk or in streaming, configuration, which probably which included stuff like, okay, from what AWS account people will send data to us. Bulk export service on its end had another configuration for S3 exports, and properties such as, okay, what automation to apply, what format the data should be in. Similar will be with real-time API service as well. So it's another bit of metadata. And if you probably see, there is something missing in the picture, and that's because all those concepts were tied together with a single entity, such as producer or consumer data set, because all those configurations were all applied to those three entities, which we put in the kind of core of the metadata platform. And yeah, I also didn't include permissions here in this talk, but permissions is another service we built to handle permissions to the dataset in self-service manner. Excluded for the talk to make it a bit smaller, but yeah, it's another bit we had here. So we needed basically a new service, which will be the core of the platform, which will handle producer, consumer, and dataset metadata, all of this metadata. We call it register service. So remember, coming back to this picture, we have a bunch of control planes. What we also need to do is to build another service to handle central metadata for the platform. Register service. So register service responsibility would be to manage a list of producers and consumers, store schemas, also take crucial parts such as schema evolution was also handled in register service. Part of the problem with register service solving is that the schema evolution, where you need to check if the changes to the JSON schema backwards compatible or not, will now be automated in business logic of their service. It also stored other ownership metadata such as emails, team names, and their ticket inbox, so people could find the teams quicker. Yeah, both Alice and Bob can use Portal, and Portal under the hood will query registered service API. The service itself architecture is relatively simple. Again, API gateway, Lambda functions, DynamoDB is quite common patterns for serverless backend services in AWS. I'm not going to dive into that a lot too much. Okay, so, but as we mentioned before, we know that data sets, producers, consumers, all of those names and schemas need to be used in other control planes. So how we'll move this information? We have microservices, so each service will have its own database or something like a database. How do we move this data around? So obviously one pattern which we could see here is maybe register service will, whenever anything changes in producers, consumers, so data sets, maybe we'll call every other service downstream, like ingestion service, data lake, and bulk expert, and tell them that, well, this data set was created, please apply the changes, and then wait until the changes are executed synchronously. That's will be a problem for us as we saw it back then, because again, it doesn't align well with microservice architecture. So we register service will get tightly coupled with other control planes, and whenever we want to add new services and new features, we'll need to make changes in register service if something doesn't really well align with our microservice architecture. So the approach we did was put an event bus in between. Event bus was implemented as a AWS service event bridge, which we really liked. So we would send events to this event bus with metadata. By the way, I use blue color to distinguish metadata. Well, not on our diagram, but you see on the next ones. So we'll send the metadata in the event bus, and a bunch of other control planes, or maybe even our customers, can subscribe to it and track the changes in metadata and use this data to make changes on their own services. We will dive into how exactly it works further down the presentation. These patterns, which we discuss here, this and this, could be referred as orchestration and choreography software patterns. This will be referred into like orchestration, where the register service behaves as an orchestrator and talks to every other control planes directly. And this is more like a choreography patterns, where every control plane knows what to do with their events in the system on their own and behaving a bit more independently. If you want to know more about this, there is a nice article which I linked here in the bottom. Let's take a look at data lake as an example of how it transformed with self-service architecture. So before that, as you remember, we had data flowing in these 3 buckets. We had code repository, which created Google Catalog, which was used by Fina and other services. So let's take a look right now. So remember there was software application sending data to ingestion service. Data was in the ingestion service came to real-time S3 buckets, stored there as JSON events. There was a Glue catalog. Okay, so now we're adding a portal where Bob, as the data producer, will create a dataset. This dataset will flow through register service and to the event bus. All the information about dataset, the schemas, the names, all of this will be there. So now we need to apply the Glue data catalog. And so what we added is added a Lambda function, which would receive the event through event bridge about dataset and update the Glue catalog. So in this example, it will create a Glue table. So as you see, we have data lake, and we're basically adding 2 separate flows. One with data that contained actual real data from the dataset, like actual records and events. And another one is the metadata, which is like data sets information such as schemas and names and so on. So we basically could split almost every service in 2 parts: the data plane, which handles their dataset data, and the control plane, which handles metadata and applies any changes to data plane if needed according to their control metadata updates. Let's take a look at another example. So in this case is bulk expert service. So as you remember, before that, it was getting the data from a S3 bucket, snapshotting, transforming it, and putting it in another bucket in a different format, better suited for external consumption and sharing with data consumers. Code repository was here used to orchestrate the jobs. So we will create triggers and chain the jobs all together based on what customers defined in the code repository. Now, well, we already know what data plane is, so we know that the data plane will be almost unchanged. It will contain a S3 bucket, it will have the glue jobs, and flow. It will manage the flow data from one bucket to another. Let's in a similar fashion track the metadata. So in this case, Bob will use Portal to configure S3 expert. So it will say, okay, I want to export this data set to S3. Clicks on Portal. Portal will then talk to control plane API gateway. So in this case, bulk expert service will have its own API because it needs to track the changes to S3 configurations. And yeah, there'll be a Lambda as a compute to handle those incoming HTTP requests and configure the jobs accordingly. So yeah, if there is a new dataset expert, the Lambda would create a new trigger for the glue job for Spark cluster to handle this dataset from S3 bucket. Well, you'll say, okay, how about register service? But remember the case where provider datasets are updated. So imagine that dataset is deleted. And a dataset is deleted means that in this case, we need to terminate the jobs, remove the triggers, update our orchestration. So again, there's to be another Lambda that will be listening to events from event bus and deleting the triggers where needed on those events asynchronously from changes in register service. A bit UI. So yeah, unfortunately, I cannot show you the demo because it's built internally. But all I can share with you is screenshots which don't have any confidential information. So as you see here, this is a page of the dataset. We had versioning because it's what was a part of the schema evolution. You will see here we had this name of provider, the dataset, description, some metadata such as ingestion formats, if the dataset was exported or not. And you will see here multiple tabs, and those tabs we usually put all those different control planes and services with the features that the services supported. So you'll see there is a separate one for schema, for bulk ingestion, for access, equality, and for expert as well, which in this case refers to bulk expert. A bit of how the schema looked like. So right now customers could open the UI and view their schema not in the code repository, but in a beautifully beautifully formatted table as right here. So we have like all the list of properties and other metadata as well. If people want to, they can always toggle the JSON format as well. But yeah. So we're getting to the end. So results and lessons learned. So yeah, we launched self-service successfully. We onboarded tens of new teams, hardened more data sets. The main win for us, the teams can now create data sets in minutes, build data integration in days. The whole project pushed us to update the documentation, even better to document the process as much as possible to help the teams to integrate with each other in self-service manner. Teams will still reach out to us, of course, but much less compared to the number of customers that we had. We migrated some of the existing customer base to self-service dataset management, only some because we build the features in self-service support one by one. So if the customer would still use something like real-time API vending of their dataset and it's not currently supported for self-service, we won't be able to migrate this customer to self-service management. But all the new customers will flow through the new platform. Catalog accessible in Pixie Desk Portal was a large win for us. It simplified the customers' interactions with data platforms. Now the managers, the business analysts, a bunch of other non-tech people could refer to datasets, explore datasets, search for datasets, discover datasets, and all their dataset metadata in UI, and don't use the code for that. And I mentioned before, Portal also allowed us to bring more UI features like metrics for access, data quality, and so on, and build more experiences. So control planes will have APIs that allowed the portal to interact with the backend. Those APIs can also be exposed to developers to declare datasets in infrastructure as code. That's another feature which we considered like an opportunity, but we haven't done yet. So yeah, because we now have APIs, we can build more automation on top of what we have in the portal. and provide maybe even better experiences to developers. Other results is, so event-driven architecture simplified also building audit services. So audit service would be the one that will store all those different events about metadata and display those as past user actions in the UI. It was quite useful for helping customers to understand what changed, how the set changed over time, what metadata has evolved, and so on. So we will display this in the portal. And because we would use event-driven architecture, all what the service needs to do is just to store all those events, and adding new services and features would be relatively easy. Nice feature about EventBridge or archive, which would store all the published events for a period of time. Allowed us also to delay investment in Redrive and backfill infrastructure for this event-driven architecture. So in case there was an issue in control plane, we would need to fix, we could use this archive feature of EventBridge to republish all their events, which we found quite useful for us. Yeah, further ahead is microservice architecture helped us to streamline development across 12 engineers that were building this project. The number was different from time to time, but our team didn't grow as fast as we expected due to other reasons which are not in our control. So yeah, well, maybe, yeah, there was definitely we saw a boost of productivity, but also the cost was also there because we need to set up all the services from ground up. And even though the registered services control plane seemed technically simple, as I described, there usually not so many components involved. The business logic we kind of knew what it should look like. In reality, if it's simple, it doesn't mean it was easy to build, or it doesn't mean it will be fast to build, because we how to hype our quality bar, and yeah, building software takes time. So that's something that I personally learned, that if low-level architecture is simple, but you still need to think through all the details, all the bunch of different API endpoints, the database interactions, so on, which will take time to build. After we built our own catalog and portal, there was a new service that released by AWS, which is called DataZone. So DataZone is a AWS service which helps you to discover and share data at scale as organizational boundaries with governance and access controls. Sounds a bit familiar to what we were building. Yeah, again, it's not exactly had the same feature set as what we provided, but it was there. It didn't exist at the time we were building the portal. And it's maybe a good indication that we are on the right track in terms of, that we need actually to have UI to display the dataset catalog, and we need some like UI to help the organization to manage its data. But maybe we could have explored simpler solutions and potentially find a good integration with DataZone and save us some time. What's next? Oh, so we still face some problem with adoption. And main reason why we think so is because onboarding requires producer to ingest the data. So remember, Pixie stores all the data in its S3 bucket. That's particularly important for organizations that have their own data lakes and data platform teams. For those organizations, for those data lake teams, they might want to share the data to us to use some of our features, for example, data quality metrics. But building pipelines, data integrations just to move data from one place to another would take them a lot of time, and there was little incentive for them to do so. The data would be just data proliferation. So yeah, it was still challenging for us. And because of the high cost of onboarding, even though it was simplified, we reduced further with self-service, our catalog was still incomplete. So we didn't onboard everybody in people experience technology as we wanted. Cost of onboarding was high because teams need to integrate the data with us. And as a result of that, data producers won't bring all the data sets and keep the data sets up to date, because to actually update the data sets, they need to spend time. And if there's no direct incentive for them to do so, the catalog will be, as a result, out of date. And because of that, consumers, data consumers, and all the teams will have lower visibility in what data is available in your organization. And with applications, yeah, we need to still think about the application of that, but it means that data discovery is basically a bit harmed. So one of the next features which we're considering, but again, without me, unfortunately, because I moved to a different team, is allow registering Glue catalog in Pixie DOS without bringing the data. So if you remember, a Glue catalog is a service which handles tables and databases, just metadata about the data sets. So other data lake teams in our large organization had those catalogs, and we were considering, okay, let's support those catalogs as well. Let's allow them to be registered in Pixie DOS, but we won't ask producers to bring the data to us. So we will decentralize data, but the data will still be in different S3 buckets managed by different teams, but the metadata will be decentralized. It's a bit similar to the data mesh architecture, which I kind of linked in the below if you people interested in it. But yeah, that's the direction I think where the platform is now moving. But already without me. That's their end of their presentation. So I think we'll do some Q&A now. I'm sharing the links to my social networks, so LinkedIn, Telegram, Twitter, even though I'm not a huge poster, but feel free to rush at me on Twitter as well. If you want, you can scan their QR code, which held up the links. And with that in mind, I would love to help to open the floor for the questions.
I have a question regarding the data producer side. Um, so it was quite interesting that how you made it as a more self-service and how it enables people to connect to the or the data producers to directly serve the data and give the data over to the consumers. My question is coming around the data producer side, where let's say after the approval, where yeah, here in this picture, as Bob gives the data or gives an merge request for a specific data, and then there's a sort of a data contract that's in place where the schema of the data is already mentioned, and then you have approved for consumption via the portal. So what would happen if there's a break in that contract? So if okay, let's say if the streaming or other pipelines from the consumer side depend on that, so if there's a change in schema, this might break the further tags or pipelines that the consumers are using, right? So how essentially are you enabling the frequent changes in the schema? So does it mean that the producer has to give in the merge request as often as the change in data happens, or can anyone else who's actually owning or responsible for consuming that can also give an merge request if the schema upstream changes?
Mm-hmm. Yeah, thank you so much. So I understand the question is like about the schema on write and schema on read type of patterns and schema evolution. So it's not I didn't like talk a lot about this in our architecture in this talk, so it makes sense. So how a platform worked is, yeah, producer's responsibility was to provide, as you mentioned, some like contract, which is the JSON schema. And our ingestion API was using the schema to validate the data. So if the data was not valid, for example, it contained the field which was not present in the schema, or for example, the consumer or the producer said a field to be required, but it was not present in present in the payload which the data producer sent to us, this event would be rejected, and producer would see an error on their pipeline which would have built. They will notify the producer specifically. We took the stance for historical reasons because we wanted to protect the consumers downstream from invalid data, but we also understand that because we ask producers to provide a schema upfront, it's also another burden on their onboarding of their data sets. So it's a trade-off that we took. You mentioned, or you also asked, okay, what happens if there field like a producer wants to add new data? Producer will need to update the schema. So before self-service, the schema update would go through code repositories through code pull requests. So before this pull request was done, the consumer can producer cannot send the new data. After self-service, the schemas would be updated through the UI. So it theoretically should be faster, and that was our way to decrease the constant prose of their schema on write pattern, that even though producer has to provide the data, they can now do it through portal, which should be much faster to update the schema rather than doing it through the pull requests. You mentioned also how we make sure that the changes in schema doesn't impact their consumers downstream. So this was the process of schema evolution. So we declared the rules which are backwards compatible, which are not. So for example, we consider that removing of the field is not backward compatible change. So if a data producer wants to remove the field, they would need to create a new dataset version. It was another concept which we had in our platform. So dataset version was basically like another major version bump, basically, that producer had to do and add a new schema for this different version of their dataset. And the core part was that their dataset versions would be stored separately. So consumer would need to migrate to the new dataset versions after they are introduced. So yeah, so minor schema changes, how we call them, or backward compatible changes, could be done to the same dataset version, to the same schema. Consumer will just continue consuming the fields, like the new fields. For example, adding a field would be an example of such change. Large refactoring, schema refactoring, such as removing the fields, for example, we would require producers to create a new dataset version and send the data again for the new version of the dataset and integrate new consumers as well.
Got it.
Yeah.
Perfect. Thanks a lot for answering it clearly.
Thank you, everyone. Thank you for your attention, and yeah, have a good day.